So now we're discussing section 2.1 and 2.2, introducing the idea of derivatives, page 1. So first, let's just talk about an introduction to begin with. We need to know what a secant line is, and the definition of a secant line is a line that intersects our curve at 2 points. So we're looking at this parabola-shaped curve, and here is my purple secant line intersecting my curve at point x1 and x2, which we'll also refer to as A and B. So if we have 2 points, then we can talk about the line that creates these 2 points and specifically the slope of that line. You're familiar with the slope formula where we're using x1, y1 as our first point and x2, y2 as our second point. But really, we should progress to start using function notation, not just line notation. So we will have some input A in place of x1 and some output f of A in place of output from that piece. So we can now talk about point A and whatever its output may be, point B, which is up here, and whatever its output can be, and we can find the slope. But at this point, we're actually going to call it the average rate of change. The phrase rate of change is important, and specifically this is an average because later we're going to have an instantaneous rate of change. But it turns out when we're talking about these secant lines, we might want to talk about a lot of secant lines. So instead of talking about some second point, x2, or b as we've renamed it, let's talk about it in terms of its distance from A. So there's A, and we are h units away, which is how we arrived at B, but we're just going to focus on how many units away we're going to be. So if you take this slope formula and you plugged in A and h plus A, then your formula simplifies to this. Notice in your denominator it was B minus A, but we said B is really A plus some distance away, h. Well, the A's are going to cancel each other out and they're going to add to 0. So our denominator just has h. So the important thing to focus in, all three of these are the exact same thing. So if you're asked to find the slope of a tangent line or the average rate of change of a function between 2 points or the difference quotient of a line starting at point A and h units away, you're finding the same thing in all three cases. But here's the issue. We're not interested in a secant line. We're interested in a tangent line. So let's discuss what a tangent line is, which we usually just abbreviate TAN. It's a line that's intersecting our curve, but only at a single point, only at A. So we've got this point A, it touches the outside of our graph, and it does not intersect at another location as a secant does, or at least not in the near vicinity. So we want to talk about the slope of not a secant line, but the slope of a tangent line. Using the M notation for slope, we could use a subscript of tan, but here's the important piece. This specifically is the instantaneous rate of change, not the average rate of change, because it's not between 2 points. It's the difference between a point and essentially itself, and that's the underlying concept of a derivative. But here's our problem. You need 2 points to use the slope formula, or you at least need to know how far away the next point is. And with a tangent line, you don't have a next point away. So what we're going to do is take the information we've already learned in this class with limits, and we are going to find an average rate of change for our second point as it's getting closer and closer to the first point until they're so close, it's basically at the same place. The distance between A and this next mystery point is essentially 0. That is referred to as the instantaneous rate of change. So let's look at it in this particular example here. It's It's a little hard to see, but I've got this function f of x that was in red, and it is the graph of 0.2x squared plus 1. And I'm asked to find the slope of the tangent line, but since we haven't learned the derivative process yet, we're going to be starting at x equals 1, and then we're going to go a distance of 1 unit away, then a tenth, a hundredth, a thousandth of a distance away. So because I'm still using a slope, I'm going to come up here to my difference quotient formula, where I'm going to say, what is the distance away? Well, in this first case, we're using h has a distance of 1. But even if I didn't know that, I could have said that I'm using a, which is 1, because I was told to plug in 1. And if we're letting h equal 1, then 1 plus 1 is 2. Notice if I subtract these two numbers, I get the h of 1 that we were talking about. So I'm going to plug 2 into this function. I'm going to plug 1 into this function. And 2 minus 1, which is also my h, is my denominator. And my first slope, this purple line, is from a secant line that intersects my graph at 1 and at 2. So I've got a slope of 0.6. But we want to be closer than that. We'd rather be a tenth away. We want h to be 0.1. But notice if I took x equals 1, because that's what I was given, and I add 0.1 to 1, I get 1.1. So my second line is to go from 1 to 1.1 away, which is, well, only a 0.1 distance apart. And I'm going to plug that 1.1 into my function to get a value. And then I'm going to go back to plugging the 1 into my function, which we'd actually already done. So we already knew it was 3. Don't forget we're dividing by a new denominator. And this slope right here, going from 1 to something I can barely see, is a little bit flatter than the previous one. And so we continue this process. Now we want to use h is a hundredth of a distance away. So I'm taking the 1 I'm given, adding 1/100th to it. So I'm finding the distance between 1 and 1.01 for a slope formula, plugging it into the formulas, and I keep getting all of these different slopes. Now the numbers listed, the difference quotient, it's the slope of every single secant line, but here's what we want to look at. These numbers are all getting much closer to 0.4. So the smaller that h gets, 0.000001, we're going to find out that the slope of our tangent line is approximately 0.4.